Okay, in this part, we're going to take a look at activation functions and sort of the fundamental calculation that you're going to do to calculate entire neural networks. But we're going to break it down just into the simple calculation that you'll repeat several times as you calculate the values for an actual neural network. To look at this fundamental sort of calculation, we are going to look at three neurons. We're going to have two input neurons. I1 and I2. We're going to also have a bias neuron, B1, and we're going to have a single output neuron called O1. And we're going to see how all of these neurons interact with each other. The two input neurons are connected to the output neuron, as is the bias neuron. Now, the input to this is going to come from somewhere else. This could be the input layer of the neural network. Or there could be another layer up here. This small area will repeat itself many times in a complex neural network. And we're just seeing how we calculate for this area. So we're going to have input coming into this layer. And the bias is, it always has a input value of 1. So we'll just represent that. It's not receiving input from really anywhere else. It always just sort of has a value of 1. And that value of 1 is going to be important later on, we'll see. Now, there's also weights. There are going to be 3 weight values that we have in this section of a neural network. We will call those weight values, we'll just call them weight 1 right there, weight 2, and weight 3. Now, of those weight values, weight 1 is equal to the connection from input 1 to output 1. And this is just a value. Could be any value. Could be 0.5. These values are not constrained, these weights are not constrained to 0 to 1 or negative 1 to 1 like we've seen for the inputs and outputs of a neural network. These values can be quite large. We'll look at the second weight. Weight 2 is going to be input to output 1. And it can have another value. I'll just say 0.6. This is completely arbitrary values. And then we'll have weight 3, which is going to be equal to the bias 1. There's only one bias, at least in this small segment, to output 1 as well. We only have one output. It makes it quite easy. So those are our 3 weight values. Now, there could be, in this neural network, a second output, for example, output 2. And output 2 would have connections to all these guys, just like output 1 does. But that's outside of our fundamental equation that we're looking at here. We're just seeing how one output neuron, and this could be the output to the entire neural network, or it could be output this output can form the input to another layer of the neural network. We'll see in the next part that we repeat this several times, 3 times in fact. A XOR neural network, or an exclusive OR neural network, repeats this 3 times. So we will look at now how we're going to actually calculate this. So we want to calculate the output 1 value based on these 3 weights into it. Now the bias always has a value of 1, but it still has a weight, and that weight will change. All of these weights will change as the neural network is trained. And we'll see how neural networks are trained in later sections of this that I'm going to do. So let's see how we would actually calculate what the value of output 1 would be. Output 1 is going to be equal to the activation function. Now the activation function, we're going to see that you can have several different types of activation function. But basically we're going to just feed this entire equation that we're going to have here into the activation function. Now the activation function is going to be fed basically input 1 times this weight 1 times input 2 times weight 2 and actually these are plus, not times, plus the bias weight, which is weight 3. There's no reason to multiply that by 1. It would really be the value for bias 1, which is 1 times weight 3. So we'll simply add in weight 3. And that whole thing is passed to the activation function. We'll get to the activation function in just a second. So if we wanted to actually calculate this, we would say that output 1 equals the activation function of input 1, whatever that is. We'll say that we'll figure that we're presenting a exclusive OR type of input to this. So we'll give it a 0 and a 1. So input 1 is 0 times 0.5, which is going to be 0, plus input 2, which is 1, times weight 2, which is 0.6, plus weight 3, which is the bias weight, which is going to be 0.7. And then we calculate the equality of this, which is basically going to be 1.3. Now that 1.3 is not the final value, it's actually the activation function of 1.3. And we need to look at the activation functions that a neural network might have. There's really three very common activation functions for a neural network. There is the sigmoid, and there is also the hyperbolic tangent. The sigmoid function is equal to f of x equals 1 over 1 plus the natural base to the power of x, to the power of negative x to be precise. That's the sigmoid activation function. If we were to graph the sigmoid activation function, you would see that it has a range of numbers that is only positive. So graphing the sigmoid function, it starts out and it's kind of S-shaped, hence its name. It's not the most perfect rendition of the sigmoid function, but right at 0.5, it crosses over. So if you want to represent positive numbers primarily in your neural network, then the sigmoid function is a good choice for the activation function. And on the website, I'll put up a better graph of the sigmoid function, but that is truly its approximate shape. It's very S-shaped. The hyperbolic tangent activation function is a little more complicated, and it is truly the hyperbolic tangent is going to be equal to natural base to the power of 2x minus 1. All that over natural base to the power of 2x again plus 1. Now the hyperbolic tangent function is also somewhat S-shaped, but it is over positive and negative numbers for the output from the function. So if you're going to deal with values that are both positive and negative, then you want to deal with something like the hyperbolic tangent. Now there is also a third one called the linear function, which is just simply f of x equals x. It's really almost not an activation function. And that's used in certain cases where you don't want any of the scaling to go on. And that's primarily what we're doing, is we're scaling the number, the output, in this case 1.3, to a range acceptable for the neural network. We also take the derivative of both of these functions when we train, or at least if we're training with a propagation of errors type of training mechanism. We'll see the derivatives later. For calculation of the output, we really do not care what the derivatives actually are. So if we use a activation function of sigmoid for this, it's going to be equal to 0.79, rounded somewhat. So now we see the output for this segment of a neural network. Now if we had a more complicated neural network, like we saw in the last part, where we were going to solve the exclusive OR, and your network looked something like this, where you had two input neurons going to a single output neuron. Of course, you had biases as well. You would perform this calculation 3 times. This is the first. You would perform it to find out hidden 1. You would also perform it here to find out hidden 2. And hidden 1 and hidden 2 would then be used as the inputs, and you would do the same exact sort of procedure again, and you would calculate output 1. So you can see you just repeat this over and over and over again in a neural network to calculate the final output. We'll see how to actually calculate this entire thing in the next part.